Okay, good afternoon, everyone. I'm Michael Brandt. I'm the Deputy Lab Director and Chief Operating Officer here at the laboratory. I want to welcome you all to this is the 8th time that we've had the Berkeley Lab Research SLAM, and I have been highly managed and told that I have under 3 minutes to deliver some opening remarks. So you can score me at the end of this. So the SLAM has become one of our favorite events of the year at the laboratory. And it's a great way to round out this year's National Postdoc Appreciation Week. And so that is a good thing for all of us. And this is also an opportunity for us to come together as a laboratory community to celebrate the innovative and impactful work that you all do together as one lab in research. So for everyone joining both in person and online, thank you for being here. I also want to take a moment to thank those who made this event possible. For managing the overall program and process, the Career Pathways Office with Meg Rodriguez, Justin Placencia, Stephanie Harding, and Linda Louie. I want to thank them. Thank you. Okay, thank you. I want all applause subtracted from my time so I can keep going. As always, I want to thank the members of Creative Services and AV and IT for being here and recording this and sharing it throughout the laboratory. That's very helpful. A special thanks for those who serve as screening judges and communication coaches. It does take a lot of effort, and I recognize the effort, and there's a certain amount of stress. And is there any competitiveness in this room? Because I sense a certain degree of competitiveness. Okay, so there's competitiveness. Also, I want to thank today's judges who have a very hard job of judging between first, second, and third. And good luck. Finally, thanks to today's MCs, Umari Vasquez and Dennis Knoll. They will be joining in full regalia here in a few moments. And the SLAM gives us a chance to meet some of our postdocs and early career scientists and hear about their research. They have been challenged to summarize their research in just 3 minutes or less in a way that is understandable to a non-technical audience. I want to acknowledge the leadership shown by all of the participants chosen to step up to do the challenging but crucial work of communicating science effectively. It has always been important that scientists speak clearly and understandably about their research to a broad audience. This kind of communication requires creativity, resilience, and lots of practice. And as I understand it, there's been a lot of practice going on to get ready for this. It's no easy feat, but all of our finalists embraced this challenge and trained hard over several months to get here today. So finalists, whatever the outcome of today's competition, each of you deserves our respect and appreciation for being here. And so let's give all 12 finalists a round of applause. So finally, I'm pleased to introduce our co-hosts of Umari Vasquez and Dennis Knoll. So if you would please join me to the stage.
Hello, everyone, and welcome to Building 50. And those of you joining online, welcome to the 2025 SLAM. My name is Umari. This is my first time hosting, so please be patient with me. I needed a perfect partner in crime for today. So I searched far and wide for somebody to join me. Someone who has a brilliant mind, a keen eye for details, someone who can see all the clues and solve the mystery for what it is. So can we please give a round of applause to the Holmes to my Sherlock, Dennis Knoll!
Hey, Umari, everyone. I am so excited to be here. I just came back from Europe. I was at a conference leveling up my detective skills. Do you want to know what we learned?
I would love to know.
We learned everything about the latest tech trends, the fastest cars, and top interrogation techniques. And you see this watch?
I do see it, Dennis.
It's a particle accelerator.
Ooh.
All right, but it's time to get the investigation starting. But before we do, let's honor tradition. A tradition which has been going on for about 6 years now, and the people who have been around for this time know what comes next. Yomari, I am your MC.
And I'm your MC, Dennis.
So together we are
MC
MC
squared.
All right, before we get started, first things first. Tell us about safety, Yomari.
Yes, safety. So just so everyone in this auditorium knows, the nearest AED is around the corner as you exit the auditorium to the left. Our address is Building 50 Auditorium, Seaborg Road, and our evacuation and assembly point is H1 parking lot, which is also to the left. So what's going on for today? Today, we want to make sure that our finalists can have silence when they present. So please silence your cell phones. Only take them out if you need to send a quick text, to take a photo or anything like that. We have 12 amazing finalists, and each of them will give a 3-minute pitch. We have a timekeeper who is keeping an eye on the time. And in between each finalist presentation, the audience here can join in. There will be an opportunity for you to participate in some trivia, as well as our Berkeley Lab mystery game, as well as your turn to vote in the People's Choice Award. There is a reception over at Building 91, 3rd floor after this, so you're all welcome to join us. Of course, we want you to share our excitement. These are hashtags, and you make sure you tag us in your tweets, your Instagrams, and any other social media that we may be on. So please share your love with us on social media.
Now, usually at the SLAM, between presentations, we have trivia. This year, we are going to mix it up a little bit to stay in theme. Don't worry, we still will have trivia questions and you can still win prizes. But additionally this year, we're gonna together play a little game or a big game of Clue. We will together solve the mystery of Berkeley Lab. So during a high-profile research showcase at Berkeley Lab, a national lab, a critical experiment was sabotaged. It is unknown where the sabotage took place, but we do know it happened at exactly 11 a.m. And only 6 people had access to the experiment. And I heard these 6 people are tonight in the room with us. And it's your job to find out who did it and where did it happen. So after each trivia question, you will get a clue to solve the case. You should all have this card in your program. Please check if you have this card and maybe a pen. And this card will help you keep track and solve the case. And after the event, the people who solve the case fast will receive a prize.
Awesome. So what is up for grabs today? Well, not only do our presentations get a bragging rights for being placed in the top 3 or People's Choice, they also get a really big check and the money associated with that check. So our first place winner will get $3,000. Our second will get $2,000. And our third place winner will get $1,000, with our People's Choice gets $750. So Dennis, you want to tell me about the People's Choice Award?
Sure. After our distinguished dozen give their talk, you will have the chance to vote. If you're here in person, your ballot is in the back of your program. So you can just rip out this little card and cast your vote once all finalists have presented and you leave the room. If you're joining us from remote, we will provide a link in the chat at the end of the event, and the poll will be open for 10 minutes, so be quick. Now, that was all fun until now, but again, this is a competition, which is fun. So how will the contestants be judged? The esteemed panel of judges, which is sitting here in the front, will be judging the contestants over several things, including technical content, clarity of presentation, stage presence, and enthusiasm for presenting their work. But in less than 3 minutes, so points will be deducted if they go over 3 minutes, and that's why we have our timekeeper. So who has the hardest job tonight, Yomari?
It is our judges. We are excited to introduce our esteemed judges this year. First off, he started as a contestant, he was an MC, and now he's a judge. Please welcome Bashir Mohammed from Amazon Web Services. From here at Berkeley Lab, we have the Director of Federal Relations, Jonathan Nurse. From the Berkeley Chamber of Commerce, CEO, Beth Rosner. And from Stanford University, the Associate Vice Provost for Graduate Education, Liz Silva. From Berkeley High School and a former Berkeley research student, Brooks Trotmore. And from our sister lab at Lawrence Livermore National Lab, the communications manager, Stephanie Terza. So contestants, those are the people you're supposed to bribe before the event happened. It's a little too late now, but it's okay. Thank you so much for joining us today, judges.
Yes, all the people competing in the slam are already champions. And I have heard we have several slammers of the past in our audience. So please, slam alumni, stand up and everyone give it up for them. You're already cheering well. But first, I'm sure you can do more. And second, after all, we are a research lab. So let's make sure the clapometer is sufficiently gauged. I want everyone here to start clapping at like 20% baseline. 20%. Okay. That was maybe not the most exciting topic. Now raise it up to 40%. Go a little bit higher. Yes, we are about to get there. Now 60%. The pom-poms should maybe come out. Pom-poms maybe. Okay, we go to 80%. Now you can start stomping on the ground. Okay, and now give me 100%. Give me everything. Yes, Berkeley Lab. That is what I call a proper gauge.
So our first speaker had the most important job at their graduate school research group. They were the free food officer. I mean, come on, right? That is a very important job. From all the way from the Molecular Foundry, please welcome Badr Ilyas.
Imagine a time when your most personal information, everything from your bank details, private messages, will be available to others very easily. That sounds scary, right? Today, we rely on classical encryption to keep our data safe. However, the laws of quantum mechanics tells us that it is possible to build a machine that can crack the classically encoded data in a matter of a second. But don't worry. The very thing that is threatening your digital security could also be the same thing that will save it. So basically, for you to be protected against such quantum cyber attacks, you rather need a quantum encryption. And for that to happen, let me tell you one thing that you will need. That's a light source of a special type, a single photon emitter. A light source that delivers exactly one particle of light at a time. So physicists all around the world have realized the uttermost importance of such emitters and are actively trying to find what would be a perfect emitter. But we still don't have an answer. But so far, they have been taking anywhere between thousands to millions of such tiny emitters and trying to understand them all at the same time. Just think about it. All of you sitting here now are trying to tell me something about yourself to me all at the same time. Will I be able to understand you? Of course, no. And that's why at the Molecular Foundry, we are building a new tool that allows us to listen to each of these tiny emitters individually. And for this, we use a needle that is so sharp at the tip, and we bring it close to the material surface, the electrons from the needle will jump to the material and makes it shine. And I'm happy to share with you today that our tool is already working nicely and providing its first results. And with this, we are hopeful that we will find an answer for how and why certain materials emit single photons. And not only that, we can engineer them to make a better more reliable photon sources, so that when the time comes, all of us protected and ready with a single photon at a time. And the future is not scary anymore.
Thank you, Batter. It is time for trivia. This is your chance to win a lavish prize. Last year, over 100 names were submitted for the lab's new building, the cafeteria. What is the official name that was chosen? Please raise your hand.
I saw one hand there.
Collaboration Commons is correct. Good job. Now it's time for Clue. That is your symbol that we will be having a clue, which will lead you to pointing out this handout. Our clue today is, unfortunately, the Collaboration Commons has not been built yet, so the sabotage could not have been taken place there. It's okay.
All right, we saw the first talk, so that's a good point for me to ask. How is the remote audience doing? Can you give some love in the chat, please? Oh, that's good, that's good. All right, talking about remote audiences and the internet, our next contestant did his PhD in the same college as Tim Berners-Lee, the inventor of the web. From the physics division, Bojan Stanislaw.
High-energy physics has brought the world many technologies, from PET scans to the World Wide Web. Today, the big collider experiments, like the Atlas experiment, are at the forefront of big data. Atlas, for example, collects tens of petabytes of data every year. We're now working toward our high luminosity upgrade, and when it's completed, we expect to collect an order of magnitude more data. Until now, we've relied on a computing model called high-throughput computing. With high-throughput computing, we use many thousands of individual machines, not unlike your desktop, to run all our computing on CPUs. With the coming avalanche of data, we can no longer afford to do this. We simply must make use of high-performance computers like Perlmutter here at LBL. But there's a big difference between high-throughput computing and high-performance computing. Where high-throughput computing runs many independent tasks on individual machines, high-performance computers are designed to run gigantic simulations on thousands of machines, all working together using both CPUs and GPUs. I have been working to adapt Atlas's software to work well on high-performance computers. First, I'm using an industry-standard library to distribute events, which are our basic unit of work, across the machines. This ensures no machine sits idle waiting for the laggards to catch up. The fastest machines get given the most work. We are now able to do this with an overhead of less than 0.001%. I've also developed a method to allow us to use all of our CPUs and our GPUs simultaneously. Until now, we've had to leave some CPUs idle while we use the GPU, because the next step to run on the CPU depends on what's currently being calculated on the GPU. My method lets us start additional events to fill in the idle CPUs. Ultimately, my work will allow Atlas to make efficient use of our HPC allocations so we can successfully cope with the mountain of data we expect from the high luminosity upgrade. In the process, I've developed a model for using HPCs, which can also be applied to many other fields with similar big data needs.
Thank you, Bojan. All right, that was a great talk. Now we're coming to the next trivia question, so time for you to win prizes. What is the approximate current sequencing output from the Joint Genome Institute this year? Is it A, 800 megabytes, B, 800 gigabytes, C, 800 terabytes, or D, 800 petabytes? Okay, I'm gonna take you. Give me 4. That is,
B? B?
did you say B? Did you
B?
say B or C? Terabytes. Okay, that's the correct answer. All right. Yeah, I heard C. It's a little loud here on stage, so I heard C. I'm sure. Dr. Nick, could we get a prize, please? Oh, we have another prize. I'm sorry. All right, that brings us to the next clue. Dr. Jean Splicer was in the Joint Genome Institute sequencing lab at exactly 11 a.m. and her experiment was live streamed to collaborators. They couldn't possibly have left.
Our next speaker has always been destined for the stage. In high school, they used to play in a band that shared the same stage as Billie Eilish's brother. While that band has left and is now touring, our speaker is making their SLAM debut, which is arguably much more important. Please welcome to the stage from the Material Sciences, Guy Moore.
Again and again and again, the art's magnetic, the flow was athletic, dimensions is affected whether static or kinetic, and power past pressure and mass beyond measure, you can place somewhere ever he best.
Imagine you're watching your favorite band perform or your favorite sports team compete. You're so fixated on the show that you don't notice an enormous wave crashing over you. But don't worry, it's not a tsunami. It's the good kind of wave, the collective motion of thousands of fans. You stand, throw your arms up, and just as soon as the wave approaches you, you see it traverse all the way across the stadium. Magnetic moments and magnetic systems work in a similar way. At the atomic scale, each individual atom has its own magnetic moment, a north and a south, just like the magnet on your refrigerator. Magnetic moments ripple together, transporting information in ways that could revolutionize our electronics. Modern computers rely on pushing electrons around. This wastes energy and is the reason that your phone heats up when you get a lot of calls and texts, which people tell me is something that popular people have to deal with. This wasted energy reduces battery life and it harms the environment. What if instead we could use these magnetic waves to transport information and perform computation? Think about it. It is a matter of seconds when this wave traverses the audience. It would take you much longer to take this journey yourself, and it would be exhausting. Imagine having to push through thousands of sweaty fans. At Berkeley Lab, we're exploring these magnetic moments and how they ripple together. Some of my colleagues look at the individual atomic moments and how magnetism works at the atomic scale. Some look at the smoothed average properties, what we can see under a microscope. My job is to connect these two pictures and ask the question, when is it necessary to treat moments as individuals? And when is the collective picture more meaningful? At the supercomputer just below us, I'm actually able to run simulations and see these patterns emerge. By combining computation and experiment from the atomic scale to what we can see with our eye, at Berkeley Lab, we're exploring these magnetic waves and how they could open the door to a wave of new, exciting electronics that are energy efficient. So next time you're at a concert, enjoying the show, making every moment count, remember, we're in the lab trying to make magnetic moments literally count.
Thank you, Guy. Trivia time. In which year did NERSC move back to the Hill? Oh, I saw a hand. And she is correct. It's 2015. Woo! Time for clue. Between 10 and 12, Dr. Algorithm was installing new GPUs into Perlmutter with his team. The system was back online in a record time.
That is
Ooh.
great. Our next speaker is a passionate foil fencer. But before you ask, she did not know one day she would study microbial fencers. Maybe that was a subconscious decision. From the Joint Genome Institute, give it up for Hee-Jung Cho.
I like them moving, moving. I like them moving, moving. I like them moving, moving. We like to.
Nature is brutal. Beneath our feet lies one of the fiercest arenas on the planet, the soil. Soil is complex, full of interactions among plants, animals, fungi, bacteria, and even viruses. Phages are viruses that infect bacteria. Phages can kill their host to make more phages or sneak in their DNA and stay hidden. But bacteria are not just innocent victims. Some of the phage genes integrated into bacteria evolved into bacterial weapons that resemble phage tails. Bacteria use these weapons to stab their rivals and kill them. They can even acquire the DNA of the victim, gaining new functions. These invisible battles shape our world. Soil bacteria can make plants healthy or miserable. Forests grow strong or struggle. Two huge challenges are that we don't know how widespread these weapons are and how they affect plant health. My research is to understand how phages and these tail-like weapons shape plant bacterial interactions. Team science at our lab, providing massive experimental data, as well as the power of machine learning, allows me to solve this mystery. I am building a machine learning tool that scans bacterial genomes and hunts down phages and these hidden weapons. And the discoveries are striking. I have found thousands of these weapons, especially in bacteria, that help plants. We even caught plant beneficial bacteria stealing plant colonization genes from their victims, turning themselves into better plant colonizers. This shows how these weapons allow more beneficial bacteria to grow, improving the health of our food and biofuel crops. So, next time you see the forest on this hill, remember, beneath the peaceful greenery lies one of the most brutal battlefields on this planet. Head or no head, phages and their legacy weapons are rewriting the rules of survival for bacteria, for plants, and ultimately for us.
Thank you, Hee-Jung. I will definitely think about this when I take my next walk through the forest. All right, I'm very excited about the next trivia question, which is name 5 Berkeley Lab scientists who have received a Nobel Prize. If you get all of them right, I will personally invite you to dinner, but only one person. So who can name? Okay, we've got one person. I bring your mic up.
Chu, then George Smoot, Ernest Lawrence, Sol Perlmutter, and
The audience can help also.
and Seaborg, yeah, and Seaborg, and Glenn Seaborg, yeah.
That's awesome. Congratulations. Give it up. All right, great trivia question. Now we come to the next clue. Dr. Radiation attended the monthly Lawrence Legacy Coffee at the ALS, discussing recent advances in accelerator technology with his colleagues. He hinted at a significant discovery that could impact their research, sparking both excitement and curiosity before leaving the coffee at 10:55.
Ooh. Has anyone here ever thought that some things might just be fate? Well, our next speaker has only left the US for 30 days. And during those 30 days, he met his wife. Crazy, right? From the Biological Systems and Engineering Group, please welcome Jacob Rapp.
What do plastics, natural flavors, and jet fuel have in common? All of them can be manufactured with the help of bacteria. In nature, bacteria have evolved to eat whatever carbon was available to them to make what they need to survive. Bacteria naturally produce thousands of unique and interesting compounds. One such compound is an energy-dense liquid, ideal for use as fuel. Another is one component of a stable but biodegradable plastic. To achieve our economic and environmental goals, we at the Joint Bioenergy Institute want these bacteria to produce as much of these desirable products as possible. And ideally, we want them to do so while they eat the cheapest carbon available, especially if that carbon would otherwise be waste, like peanut shells or sawdust. But there's one core problem that stands in our way. Bacteria aren't interested in producing buckets of jet fuel for us. They would much rather produce more bacteria. The biological patterns that determine where the carbon goes in a cell are written into its DNA. Fortunately, in 2025, we don't have to accept that as a fact of life. We can reach into those cells' genomes and make a few changes. We, as bioengineers, have tools that let us make genes more or less active, delete genes entirely, or add new genes from other species. Taken together with the thousands of genes that make up a bacterial genome, we have far too many options to ever test all of them experimentally. That's where AI and my own work come in. AI tools trained with experimental data can predict what genes are most likely to be worth our time and what combinations of genetic edits are most likely to give us more of the chemical compounds we're interested in. And the best part is, when we do the experiments the AI has designed for us, we get more data, so the AI gets better and gives us better predictions in the next round. As we continue to iterate in this way, we get a positive feedback loop pointed directly towards exactly what we want: as much product as biologically possible. As we continue to iterate in this way, we can deliver biomanufactured products at ever cheaper price points, which lets us bring them to you as consumers. So the next time you see a biodegradable plastic, or you buy a lotion made without palm oil, or you step aboard a plane, you just might have bacteria and AI to thank for it.
Thank you, Jacob. That talk was golden. For trivia, the Berkeley Lab Guest House has hosted some pretty noble guests over the years. Which of these groups of laureates called it their home away from home, at least for a few nights? And it's a 25% chance if you guess. Okay, is that a hand?
Oh, okay.
It is not C, unfortunately. It is not D, unfortunately. You got 50-50. Go ahead and pick I don't know who put their hand up first.
I saw this hand,
Okay.
but yeah.
It is A. Congratulations. Can we make sure we get a prize to our friend over here? The front desk at the guest house only saw 2 people around 11 a.m. They were having coffee together, so a sabotage couldn't have taken place there.
Our next speaker is from Nepal and told me she hasn't climbed Mount Everest yet. But she grew up drinking yak's milk, and now she is here in Berkeley and working for the Biological Systems and Engineering Division. Next up, give it up for Jaya Tripathi.
This is I need them bags, all that money. You see the mask with that money.
Have you ever wondered how to pamper that demanding diva in your life without going bankrupt? Well, I have. But that diva currently in my life is none other than Her Highness, the microbes. Yes, the very same microbes we use to make biofuels. In return, they demand a princess treatment. They have to be inside these shiny, sterilized, air-conditioned tanks where they are constantly sipping a cocktail of sugars and other nutrients which has to be perfectly pH balanced. Very high maintenance, right? But also justifiable for the incredible work they do. However, the challenge is some demands are trickier than the others, such as supplying oxygen. Oxygen is about 300,000 times less soluble in water than the sugar is. So to keep those microbes chilling in the sugar water breathing, we have to pump in a lot of oxygen and stir it vigorously to keep it circulating. This pumping and stirring consumes a lot of electricity, making the oxygenation step the top contributor of the facility's total electricity cost. Now, here's the problem. Too little oxygen, microbes choke. Too much of it, we go broke. Therefore, we need that just right oxygen zone where microbes thrive and our wallets survive. That's the sweet spot I'm trying to find. But for that, I can't just play trial and error in a real facility. It's way too costly and impractical. So instead, I built a computer model, which I also sweetly like to call a BEE model. Not a honeybee, but a very buzzworthy blend of B, biology, E, engineering, and E, economics. This holistic model integrates microbial growth, biofuel yield, oxygen flow, and all the associated cost factors, allowing me to simulate them simultaneously across countless scenarios on a computer. Using this model, I tested lower oxygen flow. As expected, the microbial drama queens threw a tantrum and the yield dipped slightly. But after tweaking process setup and equipment design, I found a scenario that cuts oxygen cost and increases the net profit by almost 15%, even with the lower yield. That's the sweet spot. Not maximum oxygen, not maximum yield, but maximum value. Oxygen may be invisible, but its cost is not. My work makes it visible and optimal by bridging biology, engineering, and economics. Because at the end of the day, I don't only focus on pampering those microbial divas, I also care about scaling up biofuel science without going bankrupt.
Thank you, Jaya. I don't consider myself a diva, but some pampering after a long day of research doesn't sound too bad. That brings us to our next trivia time. The advanced light source got a taste of movie magic. Which blockbuster featured it? Was it A, Men in Black, B, Transformers, C, Star Trek, or D, Hulk? Did you see who was first? You choose.
Sir. Yeah.
Yeah, that's D, the Hulk. I'm sorry. Congratulations.
Woo!
Bringing us to our next clue. Dr. Tesla Nation, Dr. Cyclone, and Dr. Polymer were set to tour the ALS at 11 a.m. But Dr. Cyclone and Dr. Polymer arrived 15 minutes late. Dr. Tesla Nation arrived on time, as always. So who's our next speaker, Yamari?
Well, our next speaker is an expert at using a butterfly net, but not to catch butterflies, to catch wallabies, which they spent 2 years in Australia doing. From the Environmental Genomics and Systems Biology group, please, round of applause for Laura Cook. I want everyone in the room right now to take a deep breath in. Now, as you breathe out, imagine blowing on a dandelion, really pushing the air out deep from within your belly. Every breath you take, just like that one, is powered by a thin dome-shaped muscle called the diaphragm. And we take it for granted, but one of the most significant moments in our life as we enter the world is our first breath. And that first breath depends on the diaphragm. Within seconds after birth, the diaphragm contracts, forcing the fluid that fills the lungs to be expelled, and the lungs fill with air. Unfortunately, for some newborns, that first breath is not so easy. When the diaphragm doesn't fuse correctly during pregnancy, a hole can be left that disrupts the breathing. And the consequences for families are really devastating. In the US, over 30% of babies with this condition won't make it. And for the vast majority of cases, we have no idea why this disease happens. And this is in large part because we have a really poor understanding of how the diaphragm develops normally during pregnancy. This is kind of surprising, right? It's the organ that allows us all right now to continue to breathe. To understand how the diaphragm develops, we have to understand how its blueprint, the DNA, is read and interpreted by each individual cell of the diaphragm. Our research with collaborators at UC San Diego are using a powerful technology that allows us to look at not only the genes that are turned on in each cell, but also the instructions that switch those genes on and off. Using mouse embryos as a model, we've been able to now successfully measure the genes and their instructions in over 10,000 individual cells of the diaphragm. This blueprint is helping us to understand how and why diaphragm development can go wrong. We're learning about key cell types, including the nerves and the muscles that control the movement of the diaphragm, but also these really interesting cells that produce a lubricant that allows the lungs to glide smoothly over the diaphragm as we breathe. We're now working with clinicians to look at the mutations in the DNA of actual patients to understand what is causing this disease. This knowledge could help doctors to diagnose the condition earlier, improve genetic counseling for families, and may even one day guide new treatment strategies. Every first breath a newborn takes and every breath we take depends on the diaphragm, a muscle we rarely think of but could not live without. Thank you, Laura, for reminding us to breathe. Our next trivia question. The DOE's Joint Genome Institute was a combined effort of Lawrence Berkeley and what two other national labs? A, Pacific Northwest and SLAC, B, Lawrence Livermore and Los Alamos, C, Jefferson and Ames, and D, Oak Ridge in Oregon.
I saw very fast hand.
It is B, Lawrence Livermore and Los Alamos. Congratulations. Employees at the Integrative Genomics Building, Building 91, were having the annual staff party. So there was no way someone could have sabotaged the project without being seen there. Who's next?
Who's next? Our next contestant is a huge nerd for Catan, the board game. So huge, he even named his cat after the game. From the Material Sciences Division, Mark Villa-Tussel.
Imagine you are swimming in the sea, in clear and beautiful waters. Isn't that nice? But then the night falls, it's dark, and you can't see anything. I bet you like to find a lighthouse to guide you to the shore. This situation is actually very similar to our knowledge of new materials. Let me explain. With our powerful computers and new AI capabilities, we are discovering every year hundreds and hundreds of new materials with amazing properties. If we use them well, we can solve real and important problems, saving more energy in our daily lives, treating cancer and other diseases much more effectively, or even help mitigate climate change. But I said if. Navigating this sea of new materials without guidance can be difficult. It is sometimes challenging to understand why materials behave the way they do. And if we don't understand why they behave the way they do, then we just cannot use them to create new technologies and solve these problems. This is where I come in. While you might do experiments at the Molecular Foundry or solve complex equations in our lab supercomputer, I do the exact opposite of that. I understand materials by creating simple theoretical models. Like a lighthouse illuminating across a dark ocean, my models allow me to spot what's important from what's not. Let me give you an example. I recently focused my attention in a new type of materials called altermagnets that have the potential to revolutionize how we understand computers. I started by identifying what makes them so special. Then I went to my blackboard and wrote as few formulas as possible that still let me reproduce such unique properties. The result, I discovered simple yet general ground rules that govern these materials. And I use these rules to predict new and amazing phenomena. This new information is very important because now I can inform my colleagues at the Molecular Foundry about what kind of experiments to perform or which material to pick from the hundreds and hundreds available, saving them time, resources, and also from drowning in all this new material data. As you've seen, I help you understand how new materials behave so you can bring new technology to life. My theoretical work and simple models are a lighthouse in the vast sea of new materials.
Thank you, Mark. Really wants me to get one of these lighthouses for my own research. Coming to the next trivia question. Inside the beamlines of the ALS, electron bunches travel near the speed of light in a nearly circular path. To emit radiations, the particles are forced to wiggle, and this radiation can be used for the experiments. What is the name of the devices that make them wiggle? And magnets doesn't count. I saw this hand. That is the undulator. That's correct. Coming to the next clue. The security guard of the ALS was still basking in the joy of yesterday's date with his longtime crush, Dr. Polly Mayer. The evening was filled with laughter and delicious Italian cuisine, and he couldn't wait to see her again tonight. As he worked his shift, it was calm and uneventful, with only familiar faces passing by. And Dr. Polly Mayer was unfortunately not among them, allowing his thoughts to drift back to the wonderful time they shared. Who's next, Yumari?
Well, first, let me ask the audience, who here loves tiramisu? Oh, that's a lot of hands. Me too. I love tiramisu. However, our next speaker was born and raised in the town where tiramisu was invented, which means she's a little bit of purist when it comes to handmade versions of the original recipe, which is good because I will not be sharing my Costco tiramisu with her. From the Environmental Genomics and Systems Biology Group, please give it up for Martha Cerruti.
Work, 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 work. You see me heavy work, 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 work. You see me do me dirt, 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 dirt. There's something about that work, 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 work.
Food scarcity, soil erosion, human health. These are three global challenges, but they can all be addressed with one single intervention: increasing carbon storage in our soils. When our soils are rich in carbon, our plants go bigger and faster. The ground itself is more stable. And by locking carbon underground, we improve air quality, protecting our own health. Today, most soils worldwide do not hold enough carbon to meet their full potential. We need them to store more. Luckily for us, right now, right here, beneath our feet, and everywhere else in the world, there are underground communities that are working 24/7 to transform and store carbon for us. They are soil microbial communities. Fear not, they're not dangerous ones. They are just a teeny tiny version of human ones. Just like us, they organize. Some of them are like miners, and they gather raw carbon, while others are like jewelers, and they do transfer carbon into long-lasting treasures. And when they work together, they're so good at doing their job that they're responsible for about 40% of all the carbon stored in soils worldwide. That's impressive. Well, we still don't know exactly how they do it, but if we can uncover their secrets, we can harness their power and store more carbon into our soils, protecting them. And this is where my research comes in. Here, we study each microbe's role and strategy at the molecular level. In our group, we take soil samples from across the US. We extract the DNA and we sequence it. Then I can read it like a book, with each gene being a word that tells me who is there and what they might be doing. Then we take a look at the carbon molecules that are present in those very same soils to see if and how microbes actually transform them. When we put this information together, we map entire microbial networks. We learn who is working with whom and how we can support the growth of the microbial jewelers that will help us, humans, store more carbon into our soils. By doing this, we're paving the way to address food scarcity, soil erosion, and human health, starting right beneath our feet.
Thank you, Martha. Our next trivia question. The Bucket List platform at Berkeley Lab is a peer-to-peer employee recognition platform. How many bucket list points do you need to officially name a goat? Oh, come on. No one's named a goat here? Okay. It is not 2,000. I'm sorry. I saw this hand. It is B, 1,500. Woo! You're allowed to name a goat after me if you would like in the future. Die for clue. Goat farmer Jill brought the goats to the lab today. They are good friends with Dr. Cyclone, and they bowl together every Saturday. Jill saw him on site, and they talked about the game plan for the weekend.
Interesting. All right, before we come to our next speaker, let me first say you're an amazing audience tonight. Give a hand up for yourself. Talking about audiences, our next speaker was at the Coldplay concert when the viral cheating scandal blew up. But don't worry, we don't record the audience at this event. From the Energy Analysis and Environmental Impacts Division, Syed Sahlen.
It's not a matter of if, it's a matter of when. It's not a matter of if, it's a matter of when.
Imagine the power going out at a hospital, life support failing within minutes. At a data center, millions lost in seconds. At a national lab, years of research erased overnight. At your homes, your ice cream melts and you lose Netflix. The stakes couldn't have been higher. So, what do we rely on today to keep the power going? Diesel and natural gas generators. But beyond their CO2 emissions, the real challenge for these generators is fuel logistics. Here at Berkeley Lab, getting diesel up the hill after an earthquake or a major storm would be nearly impossible. It's hard enough getting visitors up the hill, but even when fuel is available, tanks run out in just a day or two. So the very systems meant to keep us safe run out when we need them the most. At this point, it looks like we need a backup for our backup. This is where hydrogen comes in. Right now, we store hydrogen in giant high-pressure tanks. That works, but they're bulky, costly, and still only last a few hours. Hospitals and national labs don't have room for football field-size storage, and data centers cannot afford that kind of overhead. So, if we want hydrogen to be more than just a science fair demo, we need more compact, affordable storage systems. That is the challenge I work on here at Berkeley Lab. I went beyond to explore new storage forms. A liquid as safe as baking soda on a shelf, and solids, two kinds, one porous, one dense, that stores hydrogen the way a battery stores energy. Charge them up, drain them down, use them again. I use them against thousands of Monte Carlo simulations to see how they hold up. It's basically like drawing every ticket in a lottery. Each ticket is a different future. Longer blackouts, demand spikes, soaring costs. Looking across them reveals not just the best or the worst case, but the full range of what's realistic. My method strips away market noise from the discovery process. So, the results? Some materials are already cheaper than compressed gas. The solid battery kind of materials, they're harder to perfect and are more expensive at current prices. But the shelf-stable liquid opens the biggest, most practical solution space. That is where we see our best chance at delivering reliable, affordable power. What it comes down to is really simple. When the grid goes down, power has to hold. Think of the Tesla Powerwall. It's a battery you put in your homes to keep your lights on during outages. The systems I study are already cost competitive with that benchmark. But unlike a home battery, these can scale to power hospitals, data centers, and national labs, ensuring life support stays on, your servers don't crash, and your research never stops, and your ice cream doesn't melt.
Thank you, Syed. Coming to the next trivia. Last month, the DOE's Caesar office and LBNL have developed a tool which uses supercomputers to simulate the motion of which natural disaster? Yes, there's a hand up there. Hurricanes? No, it's not hurricanes. It is earthquakes. You're not supposed. That's okay. That's okay. Huh? All right. That's fine. That's.
He just wanted the bragging rights.
It was the right answer. We'll resolve this after the. Coming to the next clue. The front desk saw Dr. Joe Brew having coffee at the guest house at 11 a.m. with another person. They did not know the other person, but their name reminded the front desk to look up the weather forecast for the weekend.
They say what goes around comes around. Well, our next speaker grew up with all male cousins, which she says must have driven her parents' blood pressure up. Well, now she says her two boys drive her own blood pressure up. From environmental genomics and systems biology, give a round of applause for Tasneem Frausnoon.
We've heard the phrase trash to treasure. But what if we can actually do it? Convert industrial and agricultural waste into jet fuel, pharmaceuticals, or even your smartphones using microbes? Conventionally, we convert low-value materials to high-value materials using the microbe baker's yeast, the same one that makes your bread and beer. But it struggles under harsh industrial conditions, including high temperature and the presence of toxic compounds.
These conditions are created by the raw materials used, the byproducts generated, and factors increasing production efficiency, which means it's unavoidable. And we have started looking at other yeasts. One such yeast that has superior stress tolerance is Isachenkia, a mini factory that can churn trash into treasure. However, the machinery in this mini factory, the genes and their interconnected metabolic pathways have not yet been studied. And this information is critical in engineering the species to be an effective industrial workhorse. To discover this, we employ CRISPR-I technology that uses a small sequence, the guide, which is unique to a gene. We have created 14,000 guides that targets each and every gene of the species and are screened under several stress conditions. During screening, the distribution of the guides vary. Some stay constant, some increase, while others decrease, providing us information as to which of these are irrelevant and which of these play a role in stress tolerance. Once we analyze the sequences, we can now identify the genes, map out their metabolic pathways, and understand the mechanism of its superior stress tolerance versus Baker's yeast. This enables us to optimize Isachenkia to its fullest potential, so it can be a great industrial platform that can use all types of waste and convert them into industrially relevant chemicals. We have shown that Isachenkia can use cornfield waste and convert them into citramalate, a building block that makes your smartphone screens. So yes, agricultural trash can literally build your next phone. So trash to treasure is not just a phrase anymore. With the right microbe, it is a roadmap to reimagining waste.
Thank you, Tasneem. Our next trivia question. Which 4 national labs are in the greater Bay Area? It's the same ones participating in the Bay Area SLAM. I saw this hand. Oh, which one did you see?
I saw the left hand first.
Okay.
Yep. You.
Correct. Congratulations. It's time for our second to last. Later in the day, researchers from Sandia and SLAC arrived on site for a workshop organized by Dr. Algorithm. He welcomed them on site, and after a little chat, they entered the auditorium in Building 50.
That is where we are currently. Interesting. All right, we are already at the last speaker. Can you believe that? That was so fast today. Today, he's the last in the schedule. But once our next speaker came first in a charity marathon. The catch, he was the only one wearing rollerblades. But I think that counts if you're working for charity, right? Today, he is delivering science from the Molecular Foundry. Give it up for Yashwant Balaji.
Let the sky fall when it crumbles. We will stand tall and face it all.
When you hear the words quantum computers, what comes to your mind? Complicated science? A sci-fi show? Or maybe your LinkedIn feed screaming that quantum is the future? For me, it's my dad and my friends asking if they should invest in quantum or AI stocks. So why all the hype around quantum computers? Because some of the world's problems, like drug discovery, climate change, encryption, are so complex that the fastest supercomputer would take longer than the age of the universe to solve them. A quantum computer could do it in days or even minutes. Sounds amazing, right? But if they're so powerful, why haven't we seen them solve any real-world problems yet? Because while the theory is incredible, The hardware is still catching up. So our team at Berkeley Lab is working to build robust quantum hardware. So here's how they work. Quantum computers use quantum bits or qubits to perform operations. Our qubits use superconductors, materials that carry current with zero resistance. These qubits have powerful performance, but are unbelievably sensitive to noise. Noise from materials, electronics, environment. But the worst one of all, cosmic rays. Cosmic rays are high-energy particles from outer space that can pass straight through buildings, concrete, mountains. When they hit the quantum chip, they create shock waves that can destroy the qubit's delicate quantum state. And boom, an entire computation can collapse. So what can we do about this? One option is to bury a quantum computer 1,000 meters underground. Sure, it works, but it's not practical when our computers are here at the lab, and our lab's 1,000 feet above sea level. So instead of hiding from cosmic rays, we are redesigning the very materials our qubits are made from by engineering them with a larger energy barrier. You see, traditionally, superconducting qubits use aluminum, which had a small barrier, making them easy targets for shock waves to go through. I'm now working on nitride-based materials that can have a barrier up to 10 times larger. And it's working. We made nitride qubits, and we can show that when a cosmic ray strikes, the shockwave energy isn't high enough to go through such a high barrier. As a result, more resilient qubits that are far less likely to collapse, even in a noisy environment. I'm bringing quantum computers close to solving real-world problems, and the hardware is the key. So next time when you hear the word quantum computers, think of the science that we're growing at the cosmic level and how we're raising the bar, should I say barrier, for quantum computers.
Thank you, Ashwant. That was our last talk today, which also means this trivia question is your last chance to get one of the prizes. It is National Postdoc Appreciation Week, so everyone, give your amazing postdocs a hand. As of this Tuesday, how many people are in the board of the Berkeley Lab Postdoc Association? Is it 3, 6, 9, or 20? It is 9, that is correct. And we are coming to the last clue of today. As co-chair of the BLPA, Dr. Polly Mayer was in their Zoom meeting between 10:30 and 11:30 a.m. They decided between bungee and hiking for the next social event. All right. That was the last clue. And that means you all made it. Give yourself a hand. But don't leave just yet. We have some more important final information. At precisely 4:20, so in 5 minutes, we will open the QR code for the clue game. Be fast. The first 5 winners take it all. And we will announce them right before we announce the prizes. This is only for the in-person audience, and if you will have to be present at the award ceremony to be eligible for the prize. But before we do this, let's get the finalists back on the stage for a massive round of applause. Three, two, one.
We would like to once again thank our judges for your most difficult job you're going to be having today. So we do not envy you tonight. So again, a round of applause for all of our judges. We have some special shout outs we would like to give. Some special thanks to our semi-finalist judges, our communications team, our photography and videography, Thor and Robinson team, the SLAM artwork team from Samantha and LBNL Creative Services, the audio visual with Miles and Darren, and our Careers Pathways office, Meg, Justin, Stephanie, Linda. Will you please join us on stage? You have to.
Please come on stage.
These are the people that make SLAM happen every year. So one more round of applause for everybody.
So what's next? On October 23rd, our top 3 finalists from today will compete in the Bay Area Research SLAM to get our trophy back. This year, the event will be here in Berkeley at the Brower Center. So mark your calendars.
And after that, it is time to cast your People's Choice Award. For those of you in person, remember that's that cutout at the back of your handout. There's pencils outside if you didn't grab one on your way in. On those online, there will be a link posted in the Zoom chat that you can use to vote. You have 10 minutes to vote. And after that, all voting will be done. We also have the reception in building 91, 3rd floor, just right outside if you walk down and across. The judges will be deliberating during this time, and our winners will be announced at the reception by 5 p.m. For Zoom attendees, their winners will also be on slam.lbl.gov, so make sure you cast your vote.
And don't forget to post on the socials.
And with that, we can start moving to the next area.